In section 4.1, we're going to talk about exponential functions. Chapter 4 introduces exponential and logarithmic functions. So exponential is one that you may have already become familiar with, hopefully, at least a little bit. So the idea behind an exponential function is one where we have an exponent that is a variable. Okay, so instead of our variable being the base of the exponent like it was last chapter, now the exponent is in the variable. So in some cases, this is very clear. We understand what's going on here, such as in the cases of f of 2. Okay, f of 2 is just 2 to the second power, right? We know what 2 to the second is. It's 4. But things get a little less clear when we have a decimal value in there. So let's think about how we might evaluate this, and we'll use the document camera here to kind of figure this out. F of 3.5 would be 2 to the 3.5. And still, obviously not clear yet what may be going on, but remember that 3.5 could be written as 7 halves. So now maybe we're getting a little closer to something that might make sense, because remember that if you have a fraction in the exponent, then you can rewrite that fraction as a radical. And in particular, if we have a 1/2 exponent, then that could be written as the square root of 2. So this is the square root of 2 to the 7th power. Now, that doesn't automatically mean that we know what that number equals, but at least now we can kind of make sense of what's going on, right? We have the square root of 2, and then we raise that to the 7th power. So in the calculator, we could get a decimal for it if we wanted. Square root of 2, and then take that and raise it to the 7th power. We get 11.31 something, something, something. Okay. So when our exponent is not a whole number, but it's still a rational number we can turn into a fraction, we can still, make sense of this. However, let's say we have f of pi. Pi is an irrational number, right? In fact, it's a transcendental number. It can't be written as, the square root of anything. It's its own unique thing, the circumference of a circle divided by the diameter. So how on earth do we make sense of a number like that? Well, it's very difficult to do that in an algebraic sense, but what sometimes helps is thinking about these as their graphs. So we'll look at the graphs of exponential functions in a minute, and that'll maybe help us. But just so that you're aware, if I ever ask you for f of pi, I'm not expecting you to evaluate that by hand because I'm not sure. I've nearly got my master's degree in mathematics, and I don't know how I would evaluate that by hand. So we use a computer, or we use a calculator, and we do 2 to the pi, and it tells us 8.825. Say approximately equal to 8.825. So if you're ever asked to evaluate something like that, understand that I'm not expecting you to do it by hand. All right, back to our slides here. We can define exponential functions. I want my dock go away. There we go. An exponential function is a function of the form, and I think typically on these slides I would just write that in the space there on the board. So I'll write it on the document camera in a second. But in general, let's just do that. So the general form or standard form of an exponential function would be f of x equals a times b to the x. All right, where a is not 0 and b is greater than 0 and not equal to 1. So typically a can be just about anything except for 0, and b can be any positive number, so anything bigger than 0, except if b is 1, then this becomes really boring, right? 1 to the x is just going to be 1 all the time. at least until you get to infinite values, and then things may change. But in general, A is just anything but 0, and B is any positive number except for 1. So the domain of f in this case would be the set of all real numbers. So essentially what that means is I can plug anything I want into x in that a times b to the x function. So the defining characteristic, or the key characteristic of exponential functions, is that they occur in, or they increase or decrease, I should say, in fixed ratios. So it's as if, as you go along through the x's, it's as if you're multiplying by the same value every time. So one of the things that you'll be asked to do is, given a table of values, you can take two sequential values and divide them and see if what you get is the same throughout the table. In this table here, we have values of x and we have values of f of x, and what we want to do is, as x increases, we want to see if this increases in a fixed ratio. So I've recreated the table here, and basically what I want to do is take 6 divided by 3, okay, that gives me 2, and then 12 divided by 6, that also gives me 2, and then 18 divided by 12, that's going to give me 1.5. So I can stop right there. I don't have to go any further. I can tell immediately that this is not exponential because I didn't get all the same value every time. Okay, and in fact, as soon as I get to one that's different, I don't even bother doing the 30 divided by 18, because as soon as I get a different number right here, I immediately know that it's not exponential. Okay, what we're looking for is every single one of these quotients should be the same if this function is exponential. So in this case, we conclude that it is not. All right, so when it comes to graphing exponential functions, we're going to do that by, starting out anyway, we're going to do that just by plotting some points and then sketching the graph. So because the domain of this exponential function is all real numbers, then we want to pick points that are a good, not to say good cross-section, but a decent representative of all real numbers. So by that I mean I would like to have both some negative and some positive values. Okay, f of x equals 2 to the x is our exponential function here. So we don't need a million points, but let's do these 7. And it may make sense to kind of start with 0 and do these, and then we'll work backwards and do the negative. So 2 to the 0 is just going to be 1, right? Hopefully you recall that from algebra, that anything to the 0 power is going to be 1. 2 to the 1 is 2. 2 to the second power is 4. And 2 to the third power is 8. So 1, 2, 4, and 8 on the bottom part. And then going backwards, remember that a negative exponent takes our value and flips it over. So 2 to the negative 1 is 1/2. 2 to the negative 2, that's going to take this 4 and flip it over, so that's going to be 1/4. And then 2 to the negative 3 takes our 8 and flips that over and makes it 1/8. So these are our values for our table. So what I'd like to do now is, let's try this. Because the graph will just be better, let's go to Desmos and plot these points. So we had -3, 1/8, comma, 1/8. We have -2, 1/4. We have -1, 1/2. We have 0, 1, 1, 2, 2, 4, and lastly 3, 8. So this gives us a nice sequence of points here that kind of gives us an idea of what's happening in this graph. It looks like, in fact, maybe we'll put another point out here just to get another negative and kind of see what's happening, because it looks like maybe these points are leveling out towards 0. But if we plugged another one in, like maybe -8, maybe that would give us another point to confirm that suspicion that maybe this is acting like it's got an asymptote at 0, at horizontal asymptote at 0. So let's see, 2 to the -8. 2 to the 8th is 2056 or something. I don't know. Hold on one second. 2 to the 8th. No, just 256. That's way too big. All right, so 1 over 256 would be our point. So yeah, it looks like that confirms that theory. Okay, there is a horizontal asymptote happening at 0, and then as we get into larger numbers, we see that this function starts increasing very, very quickly. So y equals 2 to the x. If you were doing this by hand, you would just connect these points, and should look something like this. Okay, horizontal asymptote at 0, and then as the values of x get large in the positive realm, this function grows very, very quickly. So that's the general shape that we're going to have for exponential functions, and that shape can occur oriented in a couple different ways, but that's kind of the good starting point. Okay, we're graphing something like 2 to the x. So some things that we want to point out about the graph we just looked at. Okay, notice that we had a was positive. Okay, it turned out on this one a was just 1. B was greater than 1, right? B was 2. B is always the part that has the exponent on it. Okay, it is the base of the exponent. So B was 2 for our graph that we just did. And in that, the domain's all real numbers, but the range, if you notice, the range was all positive real numbers. That graph that we did, in fact, we can go back to it. The graph that we created is all up here in the positive y-axis portion of the graph. Okay, it only exists for positive values of y. All right, furthermore, that this function didn't have any x-intercept. It had a horizontal asymptote at 0, and no matter what we plug into 2 to the x, we can never make that function actually equal 0. It can get really close to 0 by putting a large negative exponent on it, but it'll never actually be 0. It'll always be 1 over 2 to the something, right? Which that 1 in the top of that fraction is never going to become 0, so it's never going to equal 0. It's going to get close, but it's never going to equal 0. The y-intercept, in case you didn't notice, was a, which in our case was 1. So when we plugged 0 in, we got 2 to the 0, which was just 1. So if we had had a number in front of the 2 to the x, like 3 times 2 to the x, then the y-intercept would have become that number, would have become 3 in my little example. The x-axis is a horizontal asymptote, we mentioned that. The function is increasing, and notice that it's also 1 to 1. We talked a good bit in section 3.8, I think, about 1 to 1 functions. So notice that this, I keep doing that, but my graph is on the other tab. Any horizontal line that you would draw here would only ever touch the graph once, even though out here, if you drew a graph, if you drew a horizontal line real close to 0, it might look like it touches more than once because of how flat this curve gets, but truly it would only equal the function. It would only cross the function at one spot. So 1 to 1. And then it contains certain points that you can kind of rely on real quickly if you need to sketch a quick graph and you only need a few points. 0a will always be in there. We mentioned that a moment ago. -1, 1 over ab, and +1 ab will always be on there, which in our case, again, a was 1. So we see the point 1, 2, and the point -1, 1/2. Okay, those are reliable points that are always easy to find. And again, we have a smooth continuous graph. So let's look at a slightly different graph. I think we can probably skip the plotting points part on this one, and we'll just sketch the graph in Desmos. All right, so this time when we have 1/2 to the x, we see that the graph has basically just flipped from the graph that we had before. Okay, it's just a reflection over the y-axis. So on this one, we see that we still have a horizontal asymptote at 0, but instead of the function increasing as x gets larger, now the function is decreasing as x gets larger. And that should make sense, because what we're doing as we put large numbers on here, like 6, 7, 8, 10, we have 1/2 to the high power, and recall from your exponent rules that if you have a fraction raised to an exponent, you can take the top and raise it to the exponent, and you can take the bottom and raise it to the exponent. So that would be 1, let's take 10 for example, 1 to the 10th over 2 to the 10th. Well, 1 to the 10th is still 1, but 2 to the 10th is getting really big. So we have a fraction with 1 in the top and some really big number in the bottom, and that makes the graph get really close to 0 as x gets larger, instead of on the previous graph, x was getting close to 0 as x became negative. All right, so let's look at those properties for graphs where our b value is less than 1. Okay, so our b is this time between 0 and 1. And notice that all of these properties are the same except this one right here. Okay, everything is the same on these properties, but when you make b a fraction or a decimal between 0 and 1, the function switches to decreasing. Okay, so I didn't go one by one on these points because they're all the same except for one spot. So in your notes, however you want to try to highlight that, do that. You probably certainly don't need to write all of these things down again. All right, there is a very important value, very important number that we need to be familiar with as it relates to exponential functions, and that is the natural base e. This number has a long history dating back to the 1600s, but it wasn't. It hasn't been called e for quite that long. But anyway, this number is one of the 3 really important. I don't know. Sometimes they're called. Gosh, I forgot the name now. Pi, e, and phi or phi, depending on how you say that. Are 3 numbers that are just sort of almost like magic numbers in the math world. Pi is obviously the circumference of a circle divided by the diameter. E is this, which can actually be derived a number of different ways, but the way that Bernoulli did it here was took 1 plus 1 over n and raised it to the nth power. As n got larger and larger and larger, he noticed that it didn't just increase forever, it actually approached a particular number, and it approached this what we now call Euler's number, E. The third number is phi, and that's actually related to the golden ratio. So if you've ever, in art or in math or wherever you may have seen that, if you've ever heard of or seen the golden ratio, phi is the value that we associate with that, and so it's kind of the third magic number, if you will. But anyway, we use this e value a lot when dealing with exponential and logarithmic functions. So because e is about 2.7, we notice that it falls, actually let me turn it off. It falls right between 2 graphs. Okay, if we do y equals 2 to the x and y equals 3 to the x, okay, the purple one is 2 to the x, so it grows a little bit slower than 3 to the x does, right? 3 to the x is a little steeper, a little faster. But if we do e to the x, we see that it actually falls in between these 2 graphs. So it behaves, kind of like maybe you would expect. It's just a number like 2 or 3. It's just kind of a special number that has some interesting properties. And one of the things that's interesting about it is a thing that you'll learn in calculus, and that is that let's turn these other 2 off. The slope of this, okay, if you could find a tangent line, which the whole tangent line problem is fundamental to calculus and what we do, but it has the same slope at each point as the actual value of the function. So For example, right here at 1, at 0, 1, right, the value of the function is 1, and the slope of the function is 1. So I could actually write a tangent line with a slope of 1 that goes through that point, and notice that it acts just like a tangent line from geometry, right, where you talked about lines that were tangent to circles and they only touched in one place. Well, this line y equals x plus 1 only touches in one spot, and it's right there at 0, 1. So interesting fact, at 0, when the slope of this function is 1, the tangent line slope is also 1. We could do it again at a different point. We could say, like here at 1, sorry, not there. Here at 1, looks like about 2.7. Turns out it's 1e actually. So if I made this, I don't know what the y-intercept would be, so I'll have to do it this way. E x minus 1 plus e should work, yeah. So there we have that intersection of the two functions, right? So now I have a tangent line here at the point 1, 2.718, which remember is e. So at the point 1e, the slope of this line is e. So anyway, fun fact about exponential base e is that at every value of the function, that's actually also the slope of the function. So makes it a very valuable number and type of exponential function to deal with in calculus. All right, so next in this chapter, in this section, is the idea of compound interest. Compound interest is one of my favorite topics in this chapter because, I don't know, when you start talking about money, people tend to start listening, usually. So in this case, this illustrates a very important principle that any financial planner would tell you, and that is that when you are young, your greatest asset is time. You have lots of time before you need to be thinking about things like retirement. So if you start saving now when you're young, that time can really work to your advantage. So here's the formula for something called compound interest. The idea for compound interest is when you earn interest, either in a savings account or perhaps you're earning interest on dividends or something in the stock market, then what happens is as you earn that interest is then added to your account so that in the next term, whether it's the next month or the next year or whatever, in the next term, you're earning money on a larger lump sum than you were before. Okay, so like for example, say you put $1,000 into an account, and in that first month you earn interest on $1,000. To make the math easy, let's just say you earn $10 in interest. Okay, so you take that $10 and you put it in your account. Now you have $1,010, and you earn interest on that. So in the next period, you make a little more than $10 interest. Let's say you earn $10.10. Okay, so then you add that in. So now you're earning money on $1,020.10. Okay, so each interval you have a little more money to earn interest on, which means each interval you earn a little more interest than you did in the last interval, and boom, your money grows. Okay, and it grows not quickly at first, but over time it grows pretty quickly. So let's look at an example here. We have $1,000 that we're going to invest for 1 year. 1 year, keep in mind, at an annual rate of 10% compounded. And this is, I should have mentioned on this slide, sorry. N is the number of times we do this compounding. Compounding is where we actually take the interest and we add it to the principal. So if we could compound something annually, meaning you earn interest for an entire year and then you take the interest and put it in with the principal, so that in the second year, now you're earning on that extra money. Or we could compound it monthly. Okay, so at the end of every month, you take that money and put it in, so that in the next month, now you have a larger pool to earn interest on. You could even do it daily, and then there's a way that we can actually do it continuously. So every instant that you earn interest, you add it to the principal. So we'll look at how all those things play out, and we'll start with this. Okay, so $1,000, 10% interest. And we're just going to keep our time to 1 year for now, just to kind of see what changes when we change the compounds. But our basic formula here, switch over to the camera again, $1,000 at 10%. So we want to know how much money do we have at the end if we take our principal, which is the $1,000, and we go 1 plus R, which is 0.1. Remember, one of the things to remember here is take your rate that's given to you as a percentage and turn it into a decimal. So 0.10 or 0.1, and then divided by the number of times we're going to compound it per year. And starting out, we're just going to do annually. So I'll make a note here that this is annually. And then we take that number of compounds and we multiply it by the number of years. So just 1 times 1. So this works out to be $1,000 times 1 plus 0.1, right? This is all just going to be 1.10. So we can take our calculator, do 1,000 times 1.1. This isn't a hard calculation, but it's going to get harder. So this is $1,100, as you may have been able to figure out without the calculator. All right. Gets a little trickier as we make these numbers a little bigger. So what was next? Semi-annually, I think. Semi-annually means twice a year. So we'll take our $1,000, 1 plus 0.10 over 2 this time, okay, because we're compounding twice a year. And we'll raise that to the 2 times 1. Be careful not to write that as 2.1. It's 2 times 1. I'm trying to illustrate the multiplication. So this time, let's do 1,000, 1 plus 0.1 over 2. Raise that to the second power, $1,102.50. So when we increased our compounding from once a year to twice a year, we got an extra $2.50. So it's not a tremendous amount of money, but we didn't have to do any extra work to get that extra money, so that's always nice. Let's see, 0.10, if we're doing monthly this time, now it's 0.10 divided by 12, raised to the 12 times 1, because we're still doing 1 year. So as we get into these larger numbers, it makes sense to just do this stuff in the calculator, I think. Oops, close parentheses, raise it to the 12th, and then I accidentally have a second box there. Why can't I make it go away? Okay, there we go. That was really annoying. All right. So this is $1,104.71. Okay, so again, not a huge increase in money, but going from semi-annually to monthly, we earned about another $2.20. All right, so I think maybe you're starting to get the picture. It's not a massive increase every time we increase the compounding, but it does get better. So all else being equal, you might as well try to get the most number of compounds you can. If you're in an actual situation where you're trying to invest some money in something, the more times it's compounded, the better. Okay, to the point where at daily we have 1,105 and 16 cents. So compounding helps increase our money, but it doesn't do a huge thing. Okay, it helps a little. It's not a huge difference. So instead, let's see what happens if it's compounded continuously. And this is still not going to make a huge difference. Okay, but basically what we're saying with continuously compounded interest is it's not just every day or even every hour, but it's literally every instant that you earn interest, it immediately gets added to the principal. So it's almost like it's happening infinitely fast, if you want to think of it that way. So we have a new formula for it. A equals P e to the RT. Okay, this E is our natural base E that we just talked about. Notice that now the interest rate moves up to the exponent, and there's no longer an N because we're not there is no number of times we're doing this per year. It's an infinite number of times per year. So, so our formula changes completely. So going back to our our camera here, we have $1,000. Now this will be times e to the 0.1 times still 1 year. Okay, so let's see, this time 1,000 e to the first power. Oops, that somehow turned it on alpha. 1,000 e to the first, to the 0.1, not times to the 1, to the 0.1. We get 1105.17. So really not much difference at all between daily and continuously, but still technically, I almost missed the 1. 17. So not a big difference, but slightly better. So the thing that's really going to make the biggest difference, though, is time. Okay, so I'm not going to go back to the slides quite yet, but instead, this was all for 1 year up here. Let's see what happens if we do the same thing, but you guys are what, 17 years old for the most part? So reasonably, you would not expect to retire until maybe 60. So let's say you're going to retire at 60. Well, let's even say 55. 55. That means you've got 38 years before retirement. So let's say you had $1,000 today, and this isn't going to be, when we find this isn't going to be enough money to retire on, by itself. But this, I think, expresses the power of time and how time right now is going to work in your favor. So let's just assume we had monthly compounding for the sake of just picking something. So A would equal 1,000, 1 plus 0.1 over 12 to the 12 times, now we have 38 years. So let's see how this works in your favor. 1,000, 1 plus 0.1 over 12 raised to the 12 times 38. 44,000. $2.84. So again, not enough money to retire on, but you started with $1,000, and all you had to do to earn 44,002, or I guess you earned 43,002, right, extra. But all you had to do to earn that money was not touch this money. So that's sometimes not easy, right, to take money that you have and not touch it. But if you could be disciplined enough to start out with a relatively small amount of money now while you're young, and just not touch it for a long period of time, invest it in something that's going to earn some interest. So 10% is something you could probably get out of a mutual fund, or a few mutual funds. Maybe spread your money around a little bit just to be safe. But 10% is reasonable for a mutual fund type investment. And if you could just be disciplined enough to not touch your money for a good number of years, that money grows like crazy. So, and most people don't just invest one time and expect to retire on that. They invest continuously. So if over the course of the next, say, 4 years, okay, maybe, you get a job somewhere. So over 4 years, let's say, it was, I don't know, let's go with $10,000, right? Maybe you could earn $10,000 in the next 4 years part-time in college. So take that money and, maybe you have to work a couple extra years before you could retire. But if you could take 10,000 and do the same thing with it, now we're looking at $440,000, right? Basically, that makes sense. We just multiplied our money by 10. So $440,000 might be enough to retire on, potentially. I mean, if you're not going to live too extravagantly, that's almost $500,000. So, you'd be surprised if you have $500,000, that actually earns a good bit of interest on its own. So you can potentially retire and draw down just a little bit at a time, keep earning interest on it while the balance is still large, and you could potentially live off of that for a couple of decades. Again, not extravagantly, but the numbers we're dealing with here are rather small. So keep them, just kind of keep that in mind as you start your working life. If your company offers you any kind of a retirement opportunity, retirement package, 401k, something like that, start investing early, and you could actually have a good chunk of money before retirement. All right, last thing in this section is solving exponential equations. And solving exponential equations in this section has one key component that we need to keep in mind, and that is that if a to the x equals a to the y, then x must equal y. All right, so notice that the two a's must be the same number. Okay, it's 2 to the x equals 2 to the 5. Okay, well then x must equal 5 in order for that equation to be true. So first example for solving equations is 3 to the x plus 1 equals 3 to the 4th. So we'll switch back over to the document camera and solve this one. So 3 to the x plus 1 equals 3 to the 4. Now, because already the 3's are the same, then this tells us that x plus 1 must equal 4, so x equals 3. Okay, not too bad. I'm sure it's going to get a little trickier, right? Let's see. 5 to the x plus 3 equals 1/5. Well, yeah, we can see right away that this is not quite as easy because I don't have the same bases on the left and the right. So what I need to try to do is write one of these bases so that it looks like the other base. So I think the easiest way to do that would probably be to write 1/5 as 5 to the negative 1. And now I do have the same bases. So x plus 3 equals negative 1. Subtract 3 from both sides. X equals negative 4. Okay, so sometimes we may need to rewrite one or more bases to make it match the other one, and then we're good to go. So let's look at number 3. Number 3 is a little more complicated yet. E to the negative x squared equals e to the x squared times 1 over e cubed. So this one looks complicated, but it may not be. At least it may not be as bad as it seems. So let's see. I almost have the same bases here, but there's some kind of things going on that make this a little less obvious. So e to the negative x squared. Remember that when you raise an exponent to another exponent, you multiply those together. So this would be e to the 2x. And then this is e to the negative 3, right? And if we're multiplying two things with the same base, we add those exponents, right? So this is e to the negative x squared equals e to the 2x plus negative 3, or just e to the 2x minus 3. Okay, again, let me repeat myself. When we multiply things with the same base, we add the exponents, right? So that's how I'm able to combine e to the 2x and e to the negative 3 into e to the 2x minus 3. All right, so now I do have the same bases. So this turns into a quadratic equation now. So I'm going to solve that using, getting a little low. Solve that using any of the methods that I have available to me, such as factoring. So this would be like x plus 3, x minus 1, which would give me negative 3 and 1 as my two solutions. So it's never a bad idea to go back and check if you go plug these numbers back into the x's in the original equation just to make sure that they work. But for the sake of time, we're already dealing with a pretty long video here. I will skip that check, but you might want to do that on your own. And finally, that brings us, I think, to the suggested homework. So this is a large set of homework problems. If I remember correctly, some of it is matching graphs, I think, maybe. But I didn't look before I started this video, but I feel like maybe that 29 to 36 section might be some matching graphs. But anyway, this is definitely one of those where, I don't expect you to do every single problem. Do however much of the suggested homework you need to do in order to be ready for a skill check that will be coming next class. So thank you guys for watching this video, and please email me if you have any questions. Thanks.